So far, we have been using the default type of memory allocation provided by heap. However, heap provides more flexibility on how the memory is allocated. Let's discuss about the pinned memory first. Memory allocated by malloc is typically pageable memory, which means that it can be swapped out to disk if the system needs to free up physical memory. This makes pageable memory less suitable for use in programs that frequently transfer data between the CPU and GPU because it can result in significant performance overhead due to the need to move data between physical memory and disk. By using pinned memory, we can avoid this performance overhead. Heap host malloc is a function in the heap API that allocates pinned memory on the host. This function takes three arguments. The first argument takes a pointer to the location where the allocated memory will be stored. The second argument takes the size of the memory to be allocated. And the third argument is an optional flag that specifies the type of allocation to be made. And it is suitable for data that needs frequent transfer between CPU and GPU. Pinned memory is a type of memory that is locked in physical memory and doesn't need to be moved around. The allocated memory can be accessed by both the host and the device. The type of memory is useful when you need to transfer data frequently between the host and the device because it can improve data transfer performance. This allows for faster memory transfer and can improve the overall performance of the program. This function allows the data transfer using heap memcopy and heap memcopy async function. We use heap host free instead of free function for memory allocated using heap host malloc because the memory allocated by heap host malloc is pinned memory. Using free function to free pinned memory can cause problems because free function cannot unpin the memory from physical memory. Heap host free function should be used to properly release the pinned memory and unpin it from physical memory. Now let's look at a vector addition example using pinned memory. Here we will be modifying the vector addition example by swapping two blocks of code. Specifically, we will be changing two blocks of code in the CPU code while leaving the rest of the code unchanged. One of the changes made in the code is replacing the malloc function with heap host malloc function to allocate memory on the host for three arrays A, B, and C of size n, which will store float values. The second change block uses heap host free function to deallocate the allocated memory in the host for the three arrays A, B, and C, ensuring efficient memory management. One of the primary challenges in memory management is copying data between the host and the device memory. Copying data manually between the host and device memory can be a time-consuming and error-prone process requiring extra work for the programmer. To address this challenge, heap provides unified memory, which provides a way to avoid the extra work of memory copy between the host and the device. Unified memory is a type of memory allocation in heap that provides a single address space for both the CPU and GPU. This means that data can be accessed by both the CPU and GPU without the need for explicit data transfers between host and device memory. The heap malloc managed function is used to allocate managed memory. The function takes two arguments, a pointer to the location where the allocated memory will be stored and the size of the memory to be allocated. Unified memory provides transparent memory migration between the CPU and GPU. The memory is automatically migrated to the device when it is accessed by the GPU and migrated back to the host when it is accessed by the CPU. This makes it easier to write code that can take advantage of the GPU without having to explicitly manage the memory transfer. This reduces programming complexity. Now let's look at a vector addition using unified memory. In this example, we will be using the vector addition example again, but we will focus only on the CPU code, as the GPU code will be same as the previous example. First, we declared the three pointers A, B, and C of type float, which will store the input and output arrays. Then we call the heap malloc managed function 3 times to allocate managed memory for 3 arrays A, B, and C, each with a size of float multiplied by n. It's important to note that we are no longer allocating CPU and GPU memory separately, as unified memory is being used. Therefore, we are allocating the memory for the unified memory, which can be accessed by both the CPU and GPU. Here we are populating the input arrays A and B with values in this block of code. After that, just like the previous example, the kernel is launched on the device with grid size and block size as arguments, along with the input and output arrays and the array size. Then block device synchronize function is used to ensure the kernel execution is completed before printing the result. Finally, we print the first element of the output array C. Then we use heap free function 3 times to release the memory allocated on the device for the 3 arrays A, B, and C. One important thing to note here, we are not using free function anymore because we didn't allocate any memory on the host. Finally, we return 0, indicating the program executed successfully. We conducted a performance analysis of the vector addition implementation in heap using 3 different memory allocation methods: regular, pinned, and unified memory. Here we show the kernel execution time. Our analysis showed that the regular implementation took 3.54 milliseconds to complete, while the pinned implementation was slightly faster, completing it in 3.33 milliseconds. However, the unified memory implementation was much slower, taking 95.05 milliseconds to complete. As we can see, there is no major difference between the regular implementation and the pinned memory implementation. This is because from the perspective of the GPU, there is no difference. The data is copied to the GPU side before the kernel starts. Although not shown in the slides, we notice that memory copies are faster in pinned memory implementation. Unified memory, on the other hand, provides a single memory address space for both CPU and GPU, eliminating the need for explicit data transfer between the two. However, the execution time for unified memory can be slower than pinned memory and the regular approach due to the page fault mechanism that is required to access memory. This mechanism can introduce additional overhead that slows down execution. In conclusion, the choice of memory allocation method in heap should be based on a careful evaluation of the specific requirements of the application. While unified memory can simplify memory management, it may introduce performance overheads that make it less suitable for some applications. Pinned memory can offer better performance in some cases by reducing data transfer overhead time. However, unified memory may be more reasonable for some other workloads. Programmers should profile the execution before deploying their code. In the next video, we will talk about heap events and how they can be created to monitor the execution of a command on the GPU.